Alrighty, well, let's get started. Welcome to the PCB layout stream for my BMS design series. So, in this video, we're going to lay out the PCB for the Milwaukee M18 substitute battery. So, before we get started, I need to make a few corrections. So, one thing we're going to do first is we're going to change some resistor sizes on the schematic because I got some of the sizes wrong. I realized before, but let me show you how I decided what the PCB layout should be. So here, if you can see that, here is the pack itself. So there was a nickel metal battery down inside of it, and I'm going to take this 5-cell puck here. I'm going to take this 5-cell puck here and put it down in it. Well, the problem is, normally you would just take a board and put it up here. The problem is it has to be able to carry 30 amps. So that's not enough room to carry 30 amps. So here's what I'm going to do. I took a piece of cardboard and made a template, and I cut it, and there are some little shelves down in these plastics that held the nickel metal battery in. And so what I did was I made a template that will sit beautifully down inside on top of those shelves, and then the case top will come down and actually pinch the board in between that quite snugly. So I went ahead and replicated that in Altium Designer and made a paper template for that, and made my measurements, values, and printed it out 2 or 3 times to make sure it would fit. So I just want to go over that real quick. That's how I came up with these funky board shape that we're going to be populating. So let me pull up Altium right here, and we will get started without further ado. Now this is the funky board shape here that I was talking about. So we'll go over that in a minute, but let me change these values right here. So I made a mistake here with these values here, the cell input values, because I just threw some 100 ohm resistors in here, but they're only 0603 components. Well, the problem with that is they've got to handle 50 milliamps worth of current, and so at 3.65 volt, well, at 4.2 volts peak at 50 milliamps, that's I'm sorry, I did that wrong. 4.2 volts at 50 milliamps. That's around 200 watts. Well, these are only 1/8 watt resistors, so I'm going to need to change these out very quickly to just some, I don't know, 1206 package probably. So let me do that very quickly. I'm going to change these out to some 1206 packaged resistors. And okay, all right, that is what we needed to add in there. Now we need to change these. So I'll show you a little trick for this. You can go through and you can change all these if you want to manually. Kind of annoying. You really don't have to if you don't want to. What you can do is Tools, Update Selected from Libraries, you go Next, then you Shift and select all of these, choose Component, and then you can choose what component you want to substitute with, which obviously is this resistor. OK, and Finish, Execute Changes, and Close. And then all of these have been substituted for that different component. So if we look here at our component data, it is the 1206-7100 RL from Yago. So that's it. That's the only things I needed to update here. Again, I apologize for missing that last stream, but you needed a bigger resistance value here to handle the balance current, the internal balance current of the BMS. So without further ado, let's actually get into our PCB document. So let me close our libraries here, and I'll save both of these. Okay, so with Altium Designer, design update PCB document, and then we scroll through, make sure everything looks good. I've already done all that. However, rooms. I don't need a room for this project. You can change that in the project parameters. I'm just too lazy. But you don't need a room for this project. You're not doing anything that would require a room in this project. So let's do execute changes. Failed to add class member component R2015. All right, so we need to take a look at that here. Why did you fail to add this guy? Is it because you don't have a footprint? I thought I gave you a footprint. Let's see here. Let's see. Did I give you a footprint? I did give you a footprint. Let me just do this to make sure that this is updated. Well, this is odd, ladies and gentlemen. I've already done this once today. So that's odd. I seem to have a little bit of a glitch here in my Altium, because like I said, I've already done this once today. So let me look at these errors, and we'll just solve them together. Why not? So add D2 and add R20, which they should already be part of the project. And D21 and add all these nets together. That's odd. It's acting like they are not part of the project. So let's check. So the first thing you do whenever you have a problem like this, let's check our components first. So so the pins are correct here, so let's go to our footprint then. Let's go to our footprint and check our footprint. Pin 1 and pin 2. Okay, so it looks like the footprint and the schematic component are correct, but just to be safe, I've had to do this before, so let's remove it and then reestablish this connection and then update our schematic sheets with this. Okay. The second thing we're going to do is we're going to check that resistor that was having problems. So that is this resistor here. Again, we're going to check pin 2, pin 1. Again, we're going to check this. Oh, that is backwards. So I'm glad I caught that. I must have done that wrong. That is backwards. So let me grab that. I'm glad I caught that. But that is... So there's that, and then that connection should be correct. So let's just remove this again. Reestablish this connection with this library. Let me save the library first. I did save the library. Okay. Okay. So we're going to reestablish this connection, save this, and then we're just going to hit select all and then update schematic sheets. Okay. So now we're going to save this, update the schematic sheet again. Okay, so we fixed the resistor. The resistor has been fixed. That's good. So now we need to go to the diode and see what's wrong with the diode. So it says unknown pins and failed to add class members. So we've got the resistor fixed. It's in here. It should be in here somewhere. There it is. So we got the resistor fixed. Now we need to fix the diode. So let's see here. Is it pulling in? So this is your parameter manager. So you can see anything that's happening here. So if you look here, it says no models. If we hit show, no footprint. So let's just delete this component out. Just delete it out completely. Go to our components for our schematic library here, and we'll pull the diode back in again. So we'll do it again. Are we connected up? We are connected up. So let's do that Tools, annotation, annotate schematics quietly. What that does is that just replaces whatever designators are available with the next designator without you having to re-annotate the whole schematic. Very convenient thing to have in your schematic. But let's save that and let's see if that worked to fix our PCB document. There we go, and that did. That fixed our PCB document. Now you see how all these are green? I accidentally left in the room. So if you do an import in Altium and you see something like this where all your components are green, you probably left in a room somewhere. So delete that out and then move this diode right here. And then there we go. We are all ready to lay out our PCB. So I'm just going to take these and move these right here so they're a little bit more accessible. Okay, so here is how this is going to work. The way your BMSs are laid out, the way they're laid out, power comes in one end, goes out the other. The chipset is made to set in the middle of everything. Power comes in one end and goes out the other. So that is what we are going to do. We are going to bring power in the one end and we're going to take it out the other. In our PCB document here, power is going to come in on this end, and power is going to go out on this end. So again, back to the model I have here. Well, let me change my OBS view here back to here. So back to my model here. So if it'll focus. There we go. Power will come in this end and go out this end through the connector on the top. So the way I'm going to do that is this. So I'm going to take the main power connections, the positive and negative wires, and bring them through here. So I've got a corner here cut out of both sides of this where the plastics round out, and that'll be enough to bring through a either a 16 or a 14 gauge wire up through a main positive and a main negative, and then I have this cut out here. And that'll be where the sense wires come through in a connector, in a just a regular JST connector, and the thermistors, and those connectors will be here. Main chipset will be here. The FETs will be somewhere around in here, and then of course the main output pads will be here. So just planning out how the board is going to look and then kind of visualizing it will help you when you go to do the layout. So I'm going to do the split screen here. I'm not very good at the whole split screen thing. I never use it. It's just terrible. But in order to show everyone what's going on, that is what I'm going to do. And you get to struggle along with me because this is my stream. And I'm going to do what I want on my stream while I'm sipping my cup of Sprite. Not sponsored. So let's begin here. So the first thing I always like to do is I'm going to lay out my main power inputs. So I want to lay out this guy, this guy, this guy, and this guy. So I'm going to lay out my main positive, my main negative, my sense wire plug, and then my thermistor plug. So I'm going to lay those out. So we go part actions and then select PCB components, which is also Shift J. So that'll select your PCB components. Now you have to do this in Altium as an extra step. You go into your settings and you add in a function called reposition selected components, and that'll show up here in your component menu. Reposition selected components, and then in the order that you selected them in, they will place onto your board. So we're going to place that there, that there, that there, and that there. So I believe these have been switched, so I'll take and change those around because I want my positive up here and I want my negative up here. So what I'm going to do is I'm going to bring, again, the wire here, wire up through here, and then in the slot I'm going to bring my sense wires up in a connector, connect it here, and connect it there. So if we look here, that is what is going to happen right there. However, it looks like I have the wrong 3D model in here for these two. I'm going to be using right angles instead of verticals, but that's fine. We can still do the layout, and then I'll change out the 3D models later because it'll be the exact same footprint. So that's fine just for our layout. Okay, I'm going to do that, and then I'm going to do our main outputs here. So I'm going to do our main pack plus, then our thermistor connector for the charger that we're going to design later, and then for the main power output. So we're going to do this here, here, and here. That's what we're going to do right here. So that's what we have. These should be right angle. Again, I have the wrong 3D models in there, which is fine. I will just change that before I export everything. So this will be our main input here, and this will be our main output here. And here is where all the good bits go. So I'm sure that's what you tuned in for, is the good bits. So one of the first things I want to do is to do this: edit, move, rotate selection. I'm going to rotate it by 45 degrees. And then I can do that. And then I'm going to do the same thing here: edit, move, rotate selection by 45 degrees. Okay. And then there we go. So that way when the wire comes in, it can just come straight in, and it hasn't got to have any bends in it. So there is that, and there is that. So that'll be our main two inputs. Okay. Well, let's get started then with the chipset itself. So the first rule I want you to understand when laying out your PCB is looks is half the battle. It needs to look good. You don't want your PCB to look like trash. You just don't. Looks is half the battle. That's true. And so you want it to look good. Regardless of anything else, you want it to look good. Now, I say regardless of anything else. I mean, regardless of anything marketing or anything sales kind of thing, you want it to be functional. So my rule is first prototype is always functional. Second prototype is functional and looks good, right? So looks is half the battle. Sometimes your company doesn't care about how it looks. They just kind of want you to throw it together and be done with it. Looks is half the battle. You don't want somebody opening up your product, because somebody's going to, and saying, oh, hey, Alex designed that board and it looks nasty and it looks ugly. I don't want him designing any more of my products, because marketing was hurrying you up and sales was hurrying you up. Again, looks, you need to consider looks, functionality and looks whenever you're going to do it. All right, so we've got our main chipset in here. So let's start laying this out. What first thing I always like to do is I'm going to do my cell inputs first. Normally you do your power input first and your cell input, but I like to do my cell input first because I make it into a bank of components. So let's do this, and then this, and then this, and this. For some reason, it's not doing it in order. I don't know why it's not doing it in order. That's a little bit annoying, but not impossible. So, it did do the resistors in order. It just didn't want to do the capacitors in order. So I'm going to change my grid. I'm currently at 1 millimeter. I'm going to change it to 250 millimeters. What will be? So what I'm trying to do is I'm trying to match the pins of my IC to math to whatever grid I'm picking. We'll deal with that in a minute. So the way I usually do this is looking over here at my schematic. So these are my main cell inputs, and these are my other inputs. So what I'm going to do is rotate this. Let me just close this window here. Let me rotate this, and I'm going to rotate this just like this, and then I'm going to put these together, and then do this, and then this. I think these are too big to do what I normally do. So normally what I do is I line all these up, and they're symmetrical, so I can just take the line straight across, and it looks real good. However, I think the 1206, I usually do this with 0603s, and I think the 1206 resistors are just too big to do that with. So let me do this just kind of properly then. And we'll do that. Let me do it the way I want to, and then we'll see if the actual layout works out. If it doesn't, I will fix it. Yeah, I think that looks pretty good. So you want these to be relatively close to your chipset, but they don't have to be unless you are wanting to do a super awesome, you know, kind of, what is it? Oh yeah, a super awesome noise resistant BMS, you know. But this isn't 4 layers. This is just a normal 2-layer board. Nothing fancy, nothing amazing. So what we're going to do is go ahead and do. Oh, there we go. Go ahead and do these connections. Yeah, see, that is not going to work. How do I want to do this? I think I'm going to spread these apart a little more. So let's do this. And we're going to lay that out here. We're going to do this and this with this. And we'll do this here, and this here. I believe that'll look okay. So we'll put that array right here. Again, these are just large because of the balance current I want to use. I want to back these up a little bit to make the turn I want. So and we'll bring this straight into this guy with this guy straight off with no angles. You don't want any angles. Angles are makes your board house very unhappy with you. So no angles. Bring this straight off here, straight off into, and no angles. Then into VC2, no angles, and straight up into and then VC1, straight up into VC1. No angles. Let me see. That's not right here. Why does that say CBI and not? Oh, I have made a mistake here in my schematic. I don't know if anybody can see it. So I named this net CBI, and it's also bat minus. So I've named them 2 things. I've named the net 2 things. I don't know why it didn't throw an error for that. It should have, but I named the net 2 things. So these 2 nets should be ground. They're not. They're CBI. And so that's because of this mistake that I made right here. So let's save that, update our PCB document, and now these are bat minus the way they should be. So a little trap for people who are just designing PCBs, that sometimes net names can get you. So you need to make sure that you use a 0 ohm resistor or a net tie or something for that. Okay, so that looks okay. I'm happy with that. Let me see what it looks like in 3D. That looks okay. I'm happy with that, I think. Is everyone watching happy with that? Let me know what you think in the comments below. I always do my designators last, so I try to get the layout finished with designators in mind, but I always try to do the designators last. So there are those things. Again, the sense lines for this aren't that critical. So the sense lines for this aren't that critical. Not like you would have in a high sense analog circuit. By the way, do y'all like my nice panning around like this? That's from a 3D Connection space mouse. So these are, just a little. It's basically a multi-directional joystick that you use to manipulate 3D objects. However, it works great for paper space like this, like AutoCAD and Altium and 2D CAD applications. It works great for manipulating paper space. It really does. So that's how I'm able to pan around both in the schematic like this and in the PCB layout, instead of having to drag my mouse like this, right click and drag, is with this 3D space mouse. And then I have my buttons here. I can go to 3D layout mode if I want to, and then manipulate the board in 3D layout mode, and then go back to 2D layout mode. And then over here I have my different views and things. So pretty cool thing. Anyway, so I'm going to have a signal ground plane under here. So let me take and put that here, and then put a via here, and then let me take and put that here, and put a via here. Now I know that, I don't know why I did that. It needs to go off down if it can. I know that doing this and then deleting the little tail is not, deleting the little tail is not the right way to do it, but I'm lazy and I don't want to do it the right way. So that's just the way I do it whenever I have that problem. Instead of adjusting the grid and then so you're supposed to go to the grid you need, fix it, then go back to the grid you're working on and all that. I don't do all of that. I just delete the little tail. Okay, so let's go through right here. So I already see a problem right here. Does anybody else see the problem? Do you see this? So I have a crossover right here. All of these pins go to the opposite of all of these resistors. So I have to cross all of these, right? Well, I don't have to cross all of these. This is my design. I can do it the way I want. So what I'm going to do is I'm going to go back to my schematic. Control lets you separate a component from the nets. So Control, separate the components. Then I'm going to use Y to flip it and put it back. Then I'm going to save it. Design, update PCB document. Make sure to remove that room. Execute changes. And there you go. Now all of these are in the same physical, the same line as these. So that fixes a whole lot of things. Now, let me explain this circuit right here. So separating grounds. So if you look down here, I have my main battery ground, and then I have my sense battery ground. That is fine. Sometimes these chips don't like you separating the positives. So you see here I have a separate positive sense input from the power input. So sometimes it doesn't like that. One thing I am going to do here is I am going to delete this, and I'm going to take and put this here instead, I believe, with this sense line. So what happens if you have high current pulses? Your rails are naturally going to dip, and your ground's going to raise a little, and your positive is going to dip a little with high current pulses. It just happens, right? And so what I like to do is I like to use my sense lines from the BMS, from the battery pack, and I'll take and put in an extra positive and an extra negative. Normally you have just it tied to your main positive and your main negative, but that can cause trouble during high current pulses. So I like to separate them, put my sense positive away from my main positive, my sense negative away from my main negative. But that is what this 0 ohm resistor right here is for, just in case it doesn't like this. I can just tie everything back to battery minus where it needs to be, and it'll be and then depopulate this one, and it'll be all hunky dory. So let me do that as well. Let me just go ahead and do that. I'm going to go ahead and fix that. It's just all happy. We're a happy little family here. There are only happy accidents. There are no mistakes, just only happy accidents, right? Like Bob Ross says. So let's take and put our 0 ohm jumper here. Let me see here. How do I want to do this? I believe that 0 ohm jumper needs to be a 1206 as well, doesn't it? Both of these need to be 1206s because they have to be able to sync the current that these have to sync. So let's go back to our schematic library and create us a component here. So we are going to close this back out. We're going to go back to split vertical. We're going to back to split vertical. We're going to save this, design, update schematic, execute the changes. There we go. Now this is a 1206 resistor. So this will go to our connection right here, and then I need this other one right here that will go to right here. So we'll butt those up together, and there we go. So that will be our input section here. So let's just get started routing our input section. And then you can take and drag that up. Again, should be using the right grid. I'm not using the right grid. It's okay. So it'll be fine. I don't like the way that is right there. Let's do this. Let's do this. And then let's do this. You get to ride along for my OCD. It's a bumpy ride. It is a bumpy ride. I like that better. I like that a whole lot better. So we'll do that. Then we'll go down. And do that. That connection. That connection. That connection, and then that connection. And then we're going to make them look good. So we'll do that. And so we'll butt that up against that. Raise that up a little bit. Put that there. And raise that up a little bit. And then just like that. Okay, that's looking all right. Yeah, I'd say that looks all right. let's go to our main power for the chipset now. So we're going to go here to our AVDD and our VDD. So the AVDD, that's a reserve capacitor. So if the chip needs a little bit of extra juice, it'll pull out of that capacitor. So let's go first to R2, which is right here. So we want to put that again as close to the chip as possible. This is not a high analog sensitive chip, right? So, you know, people are going to yell at me, it's got to be as close as it can be, and you're going to end up in... But in all reality, usually BMS chips aren't very sensitive, and they are fine. They don't have to follow all the strict rules like an analog front end would for a high sensitivity circuit. Okay, they're usually very robust. The most robust chipset I've ever seen in my whole life is the BQ77915. That chip can be abused and abused time and time again, and it will just keep going. It is a trooper. It's my favorite chipset. If you want to know the truth, it's my favorite chipset, the BQ77915. It's a 4 series chipset. And I would have used it for this application, but it's just not, it's very complicated to use. Let me say it that way. It's very, it has programming and calibration, all those things. The layout for it's easy. The schematic for it's easy, but setting up the chip, there's a lot of things that go into it, and I didn't want to go through all that just for a drill battery. But maybe one day if I have an application, we'll go through and make a 40Z50 BMS together. That would be quite fun. I think that would be quite fun. So I want to go ahead and finish this side of the schematic. So I think I'm going to have to make a little bit more room right here, and I don't like this. This needs to, yeah, that looks better. Again, looks is half the battle. The other half of the battle is making it work. So... okay, so let's keep going here. Pin number 9, I put down here. That's your VSS pin. So let's just go ahead and tie that. We're going to make a. This is a. We'll just go ahead and do that under here. Because this is a TSSOP package, I'm going to stick it under it. That will be fine. There's no. So this is just a TSOP package, so I'm not worried about having things under it. However, if this was like a QFN package or something else, I would worry about having traces under it. So just a side note there, depending on what you want to look at. Pin number 10, which is SRP and SRN. All right, if you don't get anything else from this, if you do not get anything else from this live stream, you need to pay attention to this step. This step is one of the most important steps when you're designing a BMS. You need to pay attention to this one specifically. This is a very crucial circuit, this one right here. This is one of the most important circuits in this whole build, the SRP and SRN, the current sensing circuit, where you have your current source resistor and then you have the filtering for it. The important thing about this is the sense lines themselves. So let me go over here. What is this? Did I break a piece of my outline off? I did. That's where that came from right there. Let's go put that back. So I drew this outline in Altium. Took and pieced it together and measured and drew in an Altium. And let me tell you something. Drawing anything in Altium is terrible. It is the worst experience. Altium is not a 3D design tool, right? They could just give us some simple cuts and divisions and differences and those kind of things just by putting, just some lines together. It would be nice to do a difference between them, or a cut. But regardless, but I drew this in Altium. It was not fun. All right, so let's grab our current sense resistor here. So we're going to put it, let's see, our negative comes in there, our positive comes in here. They're both going to come across. So let's put it here. So let's put it right here. I believe that would be a good place for it. Right in here would be a good place for it, I do believe. Either that or right here. Right here. I'm going to stick it right here. So I'm going to do right there. So I'm going to get my sense line circuitry here. So the important thing for this is these need Kelvin connections. Kelvin connections to the battery pack. So what I mean by that is it needs to be direct connections. Kelvin means direct connections. The problem that you run into with this kind of circuit is that people will take and tie, they'll take and just tie the connections to wherever they want. The problem with that is that it measures the difference between these two pads. So I have a 1.5 milliohm current sense resistor. So it measures the difference in voltage between these two and calculates what the current is, right? If you just tie these connections right here, if you just tie it to your power ground, your bat minus here, or you just tie it to your power ground or something, so you have a copper port, so it has to sense all the way through the board, all the way through its resistor and back. So you're going to have like 3 or 4 milliohms by the time you measure it. So that's going to throw your current sensing way off. We had a contractor one time design a board, and he made that mistake, and he did that, and then it ended up being quite a fiasco. It ended up being quite a fiasco. He just tied one end of the sense line just to the ground plane instead of doing it directly to the pad of the sense resistor, and it was not a good day. It was not a good day. I'm running out a little bit of room. It's a little bit tight right here, so I think what I'm going to do is I'm going to take and drag this section back a little bit, because I've got plenty of room. So as far as space goes, when I'm putting things in, I've got plenty of room. Oh, sorry for that, but I've got plenty of room right here to take and plug this in at a right angle. I've got plenty of room inside of the plastics themselves. So I'm just going to scoot that circuit back a little bit. I probably could tighten this section up a little bit. I may need to do that. But here is our current sense resistor right here. So what I'm going to do I want to put it there? I think I'm going to put it here. I think I'm going to put our current sense resistor right here. So we need to make sure that we get it in the right way. I don't like the way that's acting right there. So I'm going to name this battery ground right here, so I can get that net name in there. I should have already had all this prepared, but I apologize. I thought last stream I got everything finished, and I must not have. So I do apologize for that. But I'm just going to name that battery ground right there. And so we'll have battery ground come in here and go out to our negative right here. The only thing is in this negative line will be this right here. Okay, so let's get back to our things right here. So we want to tie, let's go back to a 250 mil. We want to tie these to ground, and then we want to tie these to ground. You know, I'm just going to take that out to the side. It'll be fine if them two vias are close together. It'll be fine. They won't be too close. Yeah, they won't be too close. All right, and then we're going to tie all of this together. I've got it backwards. So bring that out. Just like that. Now these don't have to be the same length. They don't have to be. I've never had a problem with them not being the same length. So we'll just leave it like that. I've never had a problem with them not being the same length. So and then we'll notice this says net battery ground 1. So that is your ground. That is your ground right there. That is your ground. Your main power ground. So you definitely want to make sure that you take this and manually route it to your main ground pad of that, or else again your sensing will be completely off. You don't get anything else from this. You need to do this step. This step is one of the most important. Okay, so that's our current sensing done, and pin number 12 is your charge and discharge line. So next we'll start on our main power FETs, which are going to go right here. So our main power FETs. You know what I'm going to do? I'm going to move this whole assembly up. I think I kind of want this to be centered on the board because it looks good. Oh, I've turned off all my 3D bodies. How in the world did I do that? There we go. I kind of wanted this to be centered on the board so it looks good. However, let me think about this. I need the most space here because of the fact that I have FETs that go here. Yeah, I'm going to take and move that up. I'm going to take and change it. I'm going to take and move this up, I think, just a bit. So we do this. No, I'm going to leave that. So let me do this. Let me do that, and then yeah, I think that'll give me a little bit more room here. So let me we're doing this layout together. If anything else, we're doing it together because I am changing all sorts of things. Okay, yeah, I think that'll give me a little bit more room. So let's see how the routing is now. I think that's, yeah, all that's still completely doable. All that's still completely doable. Okay, so we'll fix these back. Come on, buddy. No, that's not what I want to do. There we go. All right. Yeah, that'll be fine right there. That will be fine right there. Okay, so that's our current sensing input right there. So I'm going to put my FETs right here. That's where I'm planning on putting my FETs. So let's go ahead and select our FETs here. Select PCB components, and we'll we'll put our FETs right here. So let's see which. So let's see here. I'm going to go ahead and enable the designators for these because I can't see which ones they are. Okay, there we go. We'll go with 0.6. Okay. So Q1 and Q2, Q1 and Q3 go here. Q1 and Q3 go here. There we go. And then Q4 and Q2 go here. Now, the important thing about this is that your FETs are back to back. So that is important, so that way current can't flow in both directions. So in case something happens, current cannot flow in both directions. So Q1, Q2, Q1, and I will adjust the rules later. So there we go for that. And they will go right. They will go right in here. So okay. So let's put in our supportive circuitry now. I hope we got enough room for all this. This is we'll have enough room for all this. We will. There's not much on this other end of the chip, so we'll have enough room for all this. So let's put in our gate resistors first and our pull down resistor. Put those in first. Okay, so how do I want to do this? Because this is the gate, and then this is where the main power is going to come from. So I need my two gate resistors. They're going to go at the gate. So they're going to go at the gates, and then this guy. R21 and R24. You're going to go at the gate, and then you're going to go at the you'll go right down here is where you'll go. That's where you'll go, right there. And then I believe this one, yeah. This one is R15. Yep. R15 will go right here. Okay. So then we'll do this, and then we'll do I always like to put my gate resistors right at the FETs. Sometimes that's not possible. And then bottom layer, we'll do there's a reason for this specific looking routing, and I'll show you what it is for in a minute, why I routed it this specific way. Well, I'll go ahead and tell you. There's going to be a copper pore right here. a copper pour across right here. And then I'm going to stitch that down through another copper pour on the bottom of the board that serves nothing but to help dissipate the heat. It is for nothing else but to help dissipate the heat. So that copper pour is going to come across here, so I'm trying to minimize any cutting that I have for that copper pour. So I'm going to take this, go back to top layer, I'm going to take this and route it up along right here and take it back to this via right here. I thought is that too close? Let me adjust my grid here. Yeah, there we go. And so I'm going to put a copper pour right here. So I want as minimal cutting as possible. Bobby Samuels, new person here. Well, welcome to the stream. Welcome to the stream. You can watch me struggle to design in front of this. I'm all nervous and I'm making all sorts of mistakes. I'm correcting them. Don't get me wrong. I'm correcting them. But I am making my mistakes. So nervous as I can be to do this. So going to route that. That is the supportive circuitry for the discharge circuit. Now for the supportive circuitry for the charge circuit. So let's go ahead and select, let's do our gate resistors first. Oh, wrong button. Let's do our gate resistors first. Sometimes it doesn't want to work. You have to click on it a few times before it'll actually jump for you. So we'll do, those are probably backwards, aren't they? Okay. So we'll do our gate resistors first. Okay. I'm planning on editing this down. I'm going to take, so like with my schematic stream, I believe I'm going to just take and cut out all the parts where I'm talking and make it reduced. Same thing with this, all the parts where I'm talking and answering questions and all that, I'll just take and cut all that out and then make it into just a streamlined, this is how you design kind of deal. I'm now learning to design PCBs too. My next project is a LIFEP. Oh, is a lithium iron phosphate charger. Small one cell, 3.2 volts. Well, that's neat. That's very neat. I've designed several 1S chargers. They're fun. They're very fun. So I've got that. My favorite chipset to use is the BQ77915. That's a great chip to use. Very robust. It's basically a fancy voltage regulator. So very robust though. Very easy to use. There we go. Select PCB components. Very robust. Very easy to use. Has LEDs and stuff. So you know your project can look good and all that. Very configurable. Can do. Oh, that's a. Oh, wait, no, I need to do it this way. Yeah, we'll do it that way. Yeah, we'll do it just like this. Very easy to use. Has LED outputs. Can do 2 amps. So, power path management included? No, it does not do power path management. It is just a regular controller, I believe. I don't know. Let me. You know what? Let me see here. The 24610. Is another very popular one. It's a little bit more expensive, but the 24610 does do power path management. In case you haven't figured out, I do a lot of Well, I use a lot of Texas Instruments chips. So, you know, R16_2. So this, and then this, and then this, just like this. And so we'll do bam, and then bam, just like that. So let's go back to doing our a charge input here. So that's pin number 13. There we go. Pin number 13. So let me explain quickly, in case you've never seen something like this. This is a protection circuit for the charge input. So what you don't want to do is when the BMS trips, you don't want anything to back feed into your chipset, and sometimes that can happen in the charge line. So that's that's blocking there to make sure that does not happen. Of course, you have that 1 mega ohm resistor, but not a lot of current's going to flow through that 1 mega ohm resistor. So, all right, we've got that there, and then let's take and just back these up a little bit so I haven't got to do a diagonal. Trace, and we'll just go straight down, just like that. So if you see me switching between trace widths, that's set inside of your design rules, and I have that defaulted for all of my projects. So that's just set in your design rules. I don't know what softwares everyone else uses, but I enjoy Altium Designer. I think it is one of the best softwares for the for professionals. Now, it's not the best software for the price. Don't get me wrong, it's expensive. I would not have this software if it wasn't for PTI. Of course, they sponsor all my videos. I get to use this software that I use for work, also for doing these videos and stuff. Special thank you to them. I said last video, and I will say it again, that if you have a company that's not willing to invest in you, that's a problem. That is a problem. So, if you have a company, come here. If you have a company that just treats you as a number, they can. That is their right. Don't get me wrong. That is their right to do that. But it is also your right to want to work at a company that doesn't just treat you as a number. I'm sure several of you are watching this right now because you want to, kind of improve yourself, right? Everybody wants to improve themselves. Maybe it's to get a raise at work. Well, you got to ask yourself, well, what am I working for? I'm not telling you to quit your job. I'm not telling you that in the least to quit your job. What I'm telling you to do is consider all the money you're making, all the money you could be making, and all those things. It's not wrong to want to chase the corporate ladder and those things, but I would strongly advise you to ask yourself in 10 or 12 years, do I want to have spent all my time while my kids grew up, while they were playing sports and all this stuff? Did I want to spend that time to make 20% more than I do now, or would it be worth sacrificing that 20% for the sake of my family? I don't know how many professionals out there who are watching this have families or even consider anything like that. I don't know. But that's just my personal opinion. I enjoy working at PTI. Now, don't get me wrong. I'm compensated well for my position. I could make more money going to the bigger companies probably, but I don't want to work for the bigger companies because they're not going to treat me like a person. They're going to treat me like a number. Just something to consider. Again, it's my stream. I can talk about what I want, right? But I don't know if any of you out there have the same opinion, or if y'all are just, what is going on here? If y'all were just sacrifice yourself for the sake of the dollar. I don't know, but it seems to be like that's the attitude going now, in at least here in the U.S., that people are don't want to be worked like dogs anymore. But I don't know. I digress. So, all right. So we've done our LD input. That is a charger present sense. No, that is your load removal input. So what it does is it measures if there's any kind of load out here on the output, and once the load is removed, it'll reset flags. And then we did our OCD pin, which I'm not sure what our OCDP pin is. I don't quite remember. What was this down here? OCDP was. I don't remember what that was for. But anyway, that was 750K. So now we get to our thermistor pin, which is pin number 18, and that goes back here to our thermistor connector back here. So we're going to need to route that. And then we have a pull-up resistor to VTB at pin number 19. So let's get our pull-up resistor here. And we're going to do our pull-up here. Normally one side of the chipset's more dense than the other. Plus we haven't got any comms, which is great. So comms has a whole thing in itself that we've got to route. So and we'll just do that because pins 20 and 21 are not populated. So I don't like that. Let's do this. Let's see. Okay, let's do this. Let's see if I can do this. Okay, and so now I can take and slip this here and do this and this. Oh. Quit. This, and then I can do this, and this, and this. I like that better. And then we'll route our thermistor. Now I've got to decide how I want to take this trace all the way to the other side of the board, and I'm going to have to do this. How many times do I want to do this? I'm going to have to do this for this connection and for this connection. So I got two connections that I need to route to the other side of the board, and I do not want to sacrifice my signal ground plane, which will come from, or my battery ground plane, which will come from this connection here. So I don't want to sacrifice that. So how do I want to do this? Let me think about this for a second. Actually, my battery minus is going to come from these connections, not from this connection, because this is a sense connection, so I don't want to mess with it. The battery minus will come from here. I think I'm going to route them over the top. I think I'll route them over the top and then come down, so that way I do not mess up any of that. So let's do that. Let's route them up and over the top where I'm going to put my signal ground plane, and so that way I do not interrupt any of my signal ground stuff. There we go. Okay. That did not mean to move that. Again, did not mean to move that. Oh, I'm on the wrong layer. That's why it's moving. Because I'm going to be putting a signal ground plane here, so I don't want to mess that up. The next section, that was the thermistor. 15, 20 and 21 are not populated. 22, pin 22 is system present, so that goes to our output connector. System present does. So let's, which pin is system present? Pin number 4 is system present. Okay, so let's, system present is your on and off switch, basically. It this data sheet says it puts it into sleep mode and out of sleep mode. It's its on and off. It's its on and off switch. So and I'm planning on putting some form of switch on this battery pack. I ain't quite figured out where I'm going to put it. It's not going to be on the board. It's going to be coming out of this connector, and it's going to be mounted somewhere. It's going to be mounted somewhere on these plastics. So somewhere on this set of plastics, I'm going to put some kind of switch. I don't know if it's going to be on the top. It probably won't be on the top, but it'll be somewhere, maybe on the back here. But there will be a switch somewhere on it to turn the battery pack on and off, because I don't want it to be sitting there and draining the battery pack down the whole time I'm trying to use it. So that's your system present, and then that ties to pack minus. That ties to pack minus in order to bring it high. Now, a smart battery chipset ties it low. This ties it high. So, so that'll tie to this rail up here. And then this is wrong. That should be power ground right here. That should be pack minus right here. So let me fix that. Let me do this. Let me do this. Let me just add that in, and then this should be tied to power ground. So my hope in the near future is that I'm going to design a charger for this. So it'll be a 5 series lithium ion charger that'll go in the same old Milwaukee housing. It'll go in the same old Milwaukee housing that that the nickel metal hydride charger was in. So that is my hope. I don't know if it'll work or not, but that is my hope anyway. So okay, design. Did I save this? Save, design, update PCB document. Execute changes. Close. Okay. So there we go. There's our thermistor. I gotta get our thermistor here. So that'll go to pack minus. So thermistor number 2, we'll bring that out. Put that in a via, and then we'll bring that. Well, no, I won't do that in a. No, we'll go ahead and do that in a via, and we'll bring that across and along with this guy. And right down here, and we'll jumper that over just like this. And there we go. That's our 2 thermistors here hooked up just like that. And then next we have 23 and 24. They just both go to ground, so we'll bring those out. We'll just bring those out straight out to ground. I should have put that, went ahead and put that into a via, and then I could have. Just not want to cooperate with me. So a quick tip also, when you're routing, try not to put traces between the pads, because it can mess up when they go to put the solder mask on it. And then also during reflow and stuff, it could bridge pins and stuff. So try not to put traces in between pads. It does mess the solder mask up. They are the same potential, so but it does mess the solder mask up. So okay, I believe that's everything on the chipset routed except for, I think, the fuse and the capacitors for the ringing capacitor. So let's do the fuse. Oh, so I'll put the fuse up here. Just put the fuse up here. We'll put it like right here. It'll look good right there. Okay, I think the last two things we got here is this set of capacitors and then this set of capacitors here. So let's figure out which ones they go to. So now one set is the capacitors for the FETs. Keeps them happy, keeps them from ringing. And then the other set is for the output, to help stabilize the output. I'm not sure. They're not really big enough to make that much of a difference, but we put them on here anyway. All right, they're not going to fit right here, and they need to go right here. This is where they need to go. So let's take... They really need to go right here. This is where they need to go. And they're not going to fit right here. What am I looking at here as far as room goes? All right. Change, and we're going to go up. If I can select everything right here, and then shift and select all this right here, we're just going to go up. 1. And so that stayed right. And then I just need to fix this and fix. I pulled this off somehow. I'm not sure how I pulled that off, but fix that right there. And then there we go. We've got a room now for that, I do believe. Let's change the grid here. Beautiful. Beautiful. Okay. And then finally for these two capacitors, and we'll just throw those, I guess, right along. Can't put them there because they'll be in the way. So what is that? System present. So we'll just do this. We'll just do this. We'll just do this. No, that's unnecessary. I can figure out a better way. So if I just, they need to really be together. They don't have to be together though. They just need to. It would be better for them to be together, but they don't have to be. So let's just, they don't have to be exactly together. So let's just not put them together then. And we'll do some large traces for these. And then we'll also do large traces for these as well. Okay, I believe that's all of our components. That is all of our components. So let's start routing our main ground planes. I believe, let me just check. I believe all the nets we got left are like power ground and battery ground. Oh, and I also forgot to add battery ground to this. So I need to add a battery ground to this ground to this cell 1 minus input right here. One thing I'm not really sure about, normally with these inputs they want you to have a capacitor back to the ground, which is the same input. Not quite sure about that one. I think that's something to do with analog circuitry that I'm not really super familiar with. So anyway, I forgot I've got to do that as well. So I need to add that to the ground. So this will be our main signal ground input, and then main heavy ground input, heavy positive input. So let's do our positive first. And I think I'm just going to do I think I'm just going to do it all. So let's just start doing this and see how she looks. Wonder how it looks just with everything covered here. Of course, a lot of this won't serve any purpose. I think I'm going to have to change. Yeah, I'm going to have to. So I need to change my design rules here. If you look and you notice that it's not, it's going to the board edges, that's because I have no board outline clearance rule. So let's see what we're going to change all these to 0.3. Apply, okay, and then we're going to go our polygon actions, report selected, and there we go. Now we have our, now we have our plane here. So yeah, I think that looks pretty cool. Again, I wouldn't do this if I was doing, you know, like a 4-layer board and I was worried about noise and all this. I would do the amount of ground plane I think I need. I would do the amount of ground plane the amount of copper pour I think I need, and then the rest of it would be ground plane. Everything ground plane, stitched through ground plane, you know. But this is just a 2-layer board, and it's just for fun. So I think having the copper here will look neat. I think it'll, once I put it on both sides, I think it'll look cool. That's the only reason I did that. For no other reason whatsoever. It serves no function. I think I need to move this up a little bit. Yeah, let's get it in the middle of the plane here. But again, we're going to do the same thing here. And we're just going to go up, up. Now, I do think going up to this corner will look stupid. So let me see what this looks like. So yeah, that's the right call. I don't think going to that corner will look good at all. Let me just check it out and see, but I don't think going to that corner will look good. Well, I don't know. Actually, it does look pretty good. Yeah, I think I'm going to leave that. I think I'm going to leave that. Maybe I'm going to move this up to where it's in the middle. Yep, that's the way I want it to look. That is exactly the way I want it to look. It looks like a spaceship now. See, it looks like a spaceship. Somebody start a sci-fi drama and throw it in it. I have just come up with your new spaceship design. There we go. And we're going to attach this to that plane. Now to our ground plane, our main power ground. This is always the most fun because your main power ground is a little bit different. So it's got to go, of course, here, and then back all around here to make it look cool. No other reason. And we're going to go battery ground right here. Okay, there's our battery ground. Again, our current sense resistor. You need to make sure that your copper plane does not swallow up your sense line. Make sure your copper plane does not swallow up your sense line. They need to be separate, or else your BMS will not recurrent correctly. Make sure they do not swallow. It does not swallow up your sense line. Okay, so there's that. Now let's go to our FETs here. So what I like to do is actually start at the FETs themselves. So I'll go. I need to change my grid. What am I on? I need to change my grid here. So I'll go all the way down, probably to here, and then we'll go down, I guess, to the board edge. Again, just cosmetics. There's no electrical benefit here. And then we'll go back up, and then like that. And then when we copper pour this, what net is this? This is net C10 underscore 2. Okay, there we go. And then when we copper pour this, we make sure that looks right. What's our clearance looking like? See, I don't like that it went between the components, so I need to adjust that. Let's see if that fixes it right there. There we go. Look at that. Fixed it. Okay. That fixed it right there. Got rid of that line that was in between there. So that's good right there. I like the way that's looking. That looks just fine. Yeah, that looks just fine. The board's looking great. Again, this is a very simple board. Very, very simple. Look how simple this board is. Not very simple at all. This is a 2-hour design board. Right, so... Okay, there's that copper pour. We'll do our trace to here. Then we'll do our copper pour here. Now, I usually, for this one, so let me widen that out a little bit. Net Q underscore 5. So before I do this, I'm going to do this. So I'm going to do... Oh, it's doing that glitch thing again, where you drag it across something and it lights up. Oh, that's annoying. Why don't we just do it here then? What I'm doing is I'm creating vias to go in the pads of the FETs. The via thing has been messing up lately. It doesn't want to do right. I'm not quite sure why, but you know. And we'll just take and copy and paste those here. Your FETs are what's going to get the most hot, right? So, you know, these are Alpha and Omega 6144s. They have 2.5 milliohms worth of series resistance to them in parallel. So you've got, you know, 1.25 per side series together. That's 2.5 milliohms. So, 30 amps, that's quite a bit of wattage you're going to drop. So, I'm going to take this this copper pour, net Q1 underscore 5. There we go. Then I'm going to take it. I'm going to copy it. Then I'm going to edit, paste special, paste on current layer, and keep net name. And then I'm going to paste it. Why will you not let me snap? Okay, I don't understand. All layers, snap to all layers. And then edit, paste special. And then edit, paste special. Paste. Well, now it's okay. Let's start over here because I think I've done messed it up. Copy, reference to this point. Go to the bottom layer, edit, paste special, paste, reference to the same point, and there we go. And so now I have a symmetrical pasted layer, a symmetrical pasted layer. So I'm going to go ahead and back that up off of that this line right here. I'm gonna go ahead and back that up a little bit. So that's just to help for heat. That is for nothing else but just to try to help a little bit of heat. That is for nothing else. All right, so let's do our power ground plane here. So we're still on our 225. All right. We're still on our 25 grid here. So let's do this. And then we'll do this, 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 this. All right. And then this. Just like that. Not too shabby for just a quick and dirty layout. Not too shabby at all. I don't need to bring this into the angle. So let me just bring it in down here. I don't want to bring it in an angle. We'll just oh, wait, I didn't need to use that big old thick trace anyway. I thought that was the capacitor. That's not the capacitor. But I don't want to bring it in an angle. Could I just bring it in? No. What? No, that's fine. That's fine right there. That's perfectly fine. Let's see how we're looking here. That don't look half bad. This don't look right. I think I need to... How do we look right there? Let's... There we go. That's even. So let's take our copper pour and bring it down. Just like that. And just like that. There we go. We have a happy, well, let's do that. I think that'll look better. Maybe bring it down the corner a little more. Just that one little chamfer, I think, will help make it. Yeah. It's a happy little PCB. A happy little PCB. So there we go. We'll put our power ground in here. And then we'll just take and put our power ground. We'll just take a tap off right there. And then for our Pack Plus, we'll just take a tap off of right here. What else are we looking at? Power ground. Oh, yes. Right, we need the sense line right here. This line needs to go directly to your power ground. Your load detection. It does not need to be influenced by any other circuitry. It needs to go direct. Okay, so now we need to route our bat minus plane, which is what I'm going to put in this entire area right here. So let me do that. We'll just start here, go here, here. Now the reason I'm doing it within this outline is because I'm going to duplicate these other planes here in a second. I'm going to duplicate these other planes and stitch them slightly, not a lot, but stitch them with the with their top layers just for heat, for nothing else but heat. Okay, and then this will become bat minus, and there we go. So what else do we have to route here? Oh yes, we got to do our two bat minuses, and then we've got to do this connection here. Any other? Nope. No, well, what is this? Oh yes, we have to do our jumper to here. So let me route that up. So this is the alternate connection to this right here is the alternate connection to the power input if this input doesn't work, and I want to get this as close to the pad as possible. That's why it's stretched all the way over here instead of putting here, because I want to get it close to the pad as possible, because under 30 amps the voltage is going to be less here than it is here, less unstable here than it is here. So I want to get it as close to the pad as possible. Okay, well, I think I am pretty happy with that. Let's unsplit this and save it before I lose it all. Well, I'm pretty happy with that. I have to admit, I am pretty happy with that. So, just a few little things I'm going to have to button up on it. Of course, I'm going to have to do all the designators and things, and I'm going to have to change these components over to right angle and all of those things. But yeah, that's just a very simple layout. Nothing major about it. Just a dirt simple layout for this PCB. That's all it was a dirt simple layout. And I'm sure there are better ways to do it. There's always better ways to do it, right? But just a dirt simple layout. So I want to thank everyone for watching this live stream, and hopefully you learned something about BMS design. Again, it's just a simple board. I mean, just a dirt simple 2-layer board. I did it sort of quick and dirty. Didn't do any kind of input calculations or nothing like that. Didn't need to. These chips really don't care much. As for the long traces and stuff, again, this is going to a drill battery I'm going to use in the shop. I'm not worried about noise or anything like that. This will be completely fine. And I haven't packed the resistors and capacitors as close as I could get them to the chipset possibly, but again, it will be fine. It's not that big of a deal for this type of chipset. So thank you everyone so much for watching this stream. You are welcome to stick around. So I'm going to go ahead and fix this board and finish it, I believe. Tonight I'm going to go ahead and throw all the designator on it and probably fix these connectors. But as far as that goes, I will be ending the stream video here. So when I go to edit it, I will edit it and end it here. But I'm going to keep streaming until I get this board completely finished and ready to order. So you are welcome to stick around for that, but that won't be part of the actual posted stream archive. So yeah, you're welcome to stick around for that. But those of you who have watched so far, thank you so much for watching. If you're going to leave at this point, then thank you. I hope you do share and like it. I do have a LinkedIn as well, and a TikTok as well, and an Instagram as well, and a Twitter profile, an X profile it is now as well. So thank you for watching. Please check out my other social medias. Again, special thank you to Protechnologies for sponsoring this video, letting me use their equipment to live stream with. So that will be the end of the official design and the official layout. So again, you're welcome to stick around if you want to watch me finish this PCB.